But life is not simple, so most of the time the problems are more complicated than just the linear separable cases. So if the dataset is not linear separable, then there are two kind of techniques here. So first, if some samples are not linear separable, then we can relax the linear separable constraint so that we can have this kind of case. So a few samples are not separable. In this case, we can use select variables. Okay, but when the distribution of the classes are not linear separable like this, then we can try select variables, but select variable is not kind of the best way. So in this case, we can use the kernel trick. Okay, we can use both actually. So first, select variables. Select variables relax the constraint of linear separability. So instead of having this one, we have another additional term, minus psi I. So when this one is between 0 and 1, then the samples are here. So again, this one is the boundary lines to get the maximum margin. But this sample and these samples are within this margin. Okay, and if this one is larger than 1, then this one is actually in the wrong side. Okay, so we want to minimize this one too. We want to minimize this error term too, while we minimize our SVM loss. This is another constraint. Psi should be positive, right? And this one is the original SVM loss, Lagrangian function. And we add another term, this one. C is a hyperparameter, so with this term, we want to minimize this one too, in addition to this one. And this equation is slightly different like this. We have psi. And this one is another constraint. So when we have a Lagrangian function, then we have another Lagrangian multiplier, gamma, and then psi. Okay. So this is the equation from the previous slide. And then we can rearrange the terms. Okay, so this one is original Lagrangian function term, and this one is the same as before, and this one is the same as before, this one is the same as before. Only these three terms are the new terms because of this psi. And then using the KKT conditions on the primal problem, so we have W and B, and also we have another derivative, and then they should be all 0. And then W is the same as before, and this one is the same as before. And by this, we have C minus alpha I minus gamma I is a 0. So with these equations, we can get the Lagrangian dual problem. And then look at this one. Lagrangian dual problem terms are the same as before. It's exactly the same as before, but the bias is different due to the different constraint. So the bias should be obtained by this one. So we have this term, okay? Only when the alpha I is less than C and greater than 0. That means psi is 0. So we are talking about these two lines. If we are focusing on these two lines, then when we check the points on this line, then the psi should be 0. This point and this point and this point, psi should be 0. And then alpha I should be positive. If alpha I is C, then the gamma I is 0. If alpha I is C, then gamma I will be 0, which means psi I is positive. So then the point is around here or here. So they are not on the boundary. So only when alpha I is between these two, then we can calculate the bias term. Okay, so the constraint is different to calculate the bias. Okay, so now we know how to use select variables. Now let's talk about the kernel trick. Okay, before using the kernel trick, we already know how to use the kernel trick from the nonlinear dimensionality reduction algorithms like kernel PCA or kernel FD. Okay, so I'm gonna just briefly talk about some kind of concept. And if you want the details, then you can check the nonlinear dimension reduction chapter, okay? So to use the kernel machine, we can imagine a nonlinear function. Okay, so let's say this input space is really complicated. Then if we have a nonlinear function phi, then we can transform all the data samples into simpler space. It could be high dimensional, it could be even infinite dimensional. But anyway, if there is a nonlinear function, and then we can have a simple space, feature space. And then many machine learning algorithms, the algorithms are based on the relations between the samples. Okay, so we don't have sample xi as it is in the middle of algorithm. So always, most of the time, we have xi in the distance function or similarity function or inner product function. In any way, we have the relationship between the samples. Okay, and then that kind of relationship can be captured by the kernel. Binary function kernel k can take the role in the feature space like this. When we have an input space, and in this space we have, let's say we have x and y, then when we apply the nonlinear function, we have a phi of x and phi of y. Then when we calculate the inner product, then this is what we have. But instead of applying this one and this one separate in a sequence, we just calculate the kernel function. So we don't have to transform all the samples. That's the trick. That's the kernel trick. Okay. Then the question is, what kind of functions can be kernel functions? So we can check this Mercer's theorem. So if a kernel function is positive semi-definite, then the kernel is actually an inner product of some space. And we don't have to know what this nonlinear function is. But we know as long as kernel function is positive semi-definite, then there is some space, and then this kernel function will work as an inner product of that space. Okay, this is one simple example of a kernel trick. So when we have two samples in the two-dimensional space, if the kernel function is polynomial kernel, then actually when we drive, then this is nonlinear function. So by defining the kernel function like this, then we are implicitly defining this nonlinear function phi. But in this case, this function is really simple, so we can actually check what is the nonlinear function. But we don't have to check this nonlinear function explicitly. As long as this function is PSD, positive semi-definite, then we define some nonlinear function, then we just believe that we know by the theorem, we know there is nonlinear function, but we don't have to check what kind of function it is. And then what kind of kernel functions do we have? So these are the popular kernel functions, polynomial kernels and sigmoid kernels, and the radial kernels. Actually, this one is most popular kind of kernels, I think. And then, more importantly, we can make kernels from kernels. So K1 is kernel, K2 is kernel. Then by sum, we have another kernel. Or by product, we can have another kernel. Okay, so we can make another kernels from kernels. And the kernels are about the relations with other points, and usually they put more emphasis on the neighbors. Okay, now we talked about the kernel tricks. And then we can apply this kernel trick to SVM too. So simply we can apply the nonlinear function, imaginary nonlinear mapping. Okay, so we will not use this nonlinear mapping, but to derive equations, so we just apply this nonlinear mapping to xi and xj. Then, as you can see here, there is inner product between these two transformed vectors, phi of xi and phi of xj. Then we can use kernel function. And then the optimal hyperplane is this one, and then W star is this, and then B star is this. Okay. So since this one is a kernel xi and xj by the kernel trick, the optimal hyperplane is this one. Okay, so look at this one. When we apply phi x, then this one is kernel. So alpha I and yi and the kernel. Okay, And then the classification of new samples xi can be done by this one. Okay, so since this one is hyperplane, when we put this x here, and then we get the y. If y is positive, then it is class 1. Otherwise, if it is negative, then it is class 2. So that's binary classification problem. And then this is the diagram of SVM. So when we have a sample x, then we just calculate the kernels. We can calculate these kernels only with the support vectors. Okay, and then we have a bias, and then we calculate the sum, and then there's the output of SVM. Okay, then the optimization for SVM. So we don't actually train this by ourselves. We just use tool. Okay, so SVM needs to solve a quadratic programming QP problem. Okay, and then there are several optimization libraries, and then we can simply use these libraries. And then these are limited to small or medium-sized problems. So there are some alternative optimization procedures, chunking and decomposition methods, and sequential minimal optimizations. Okay, so these are, I think, the beyond of this talk. So let's just use optimization libraries. Okay, and then this is the last issue about SVM. So the objective function with the select variable is this one, right? And then if we rearrange these terms, then we can rewrite this one as this one. So this one is here. We can actually slightly change this constant. And then this one is actually this one. So psi I is positive for not separable cases. Otherwise, it is just a 0. So this is an operator to take just the positive part. Okay, so this is the SVM's loss. This one is a loss, and this one is kind of regularizations. And then if you remember this logistic regression, okay, P of y given y hat, given this y hat, if the target is 1, then that is a sigma of y hat. This is the probability of the class 1 given this input x. And then probability of class 2 is 1 minus sigma y hat, and then that is actually sigma minus y hat. It's a simple calculation, so you can try it by yourself. And by this one and this one, in total, P of y given y hat is actually sigma of y times y hat. Okay, and then the negative log likelihood is this one, and this one is minus log sigma y hat, and that is log 1 plus exponential function of minus y hat. Okay, so this one is the loss, and we have this term here. So this one is logistic error. So when we draw this hinge loss and logistic error, so this red line is hinge loss, and there is a flat area, and the logistic error is a green curve. It's similar to hinge loss, but it's smooth like this. And as you can see here, it is misclassification error. Okay, so hinge loss and the logistic errors are continuous approximation of this misclassification error. Okay, and one important thing is that the flat region of this hinge loss leads to sparse solution. Okay, we don't care separated samples in SVM. We don't care these samples. They are well separated. So we care these samples and these samples. Usually there are a lot of samples around here, and there are a few samples here. So it's quite a sparse solution. So we just focus on a few samples. Okay, and the solution is a QP problem with the local minima. Okay, and it's stable without the random initialization. So there is no initialization process, and then it can be solved in polynomial time. It's really fast, and people love it. So it works really great. The mathematically is beautiful, and it works. And there are only a few model parameters. The penalty term C. Okay, and then we have to decide what kind of function we use for the kernel, and then if there is a kernel function, then there are some parameters. And then the solution is sparse, so it only involves the support vectors. So once we train this SVM, then we don't need all the other samples. As long as you have the support vectors, then that's it. And the complexity is independent of dimensions because we just calculate the kernel functions with the support vectors. That's pretty much it. Thank you.